We're going to practice with some free body diagrams now, starting with a pretty simple one. We're just going to do a book on a table. Now, don't worry, for free body diagrams, you don't need to be an artist because no matter what the object is, we're just going to represent it with a square. Okay? That's all we're going to do. So the book is sitting on the table, and the first thing that is acting on it is the force of gravity, because we're just assuming we're on Earth. So that means we're going to draw an arrow down. Now, we're not just going to draw the arrow, we're also going to label it. You'll have to excuse my handwriting, but we're going to put an F for force, and then a little bit smaller, we are going to write grav, which is the abbreviation for gravity. Now, if it was just gravity, that book would be accelerating downwards because that's an unbalanced force, so it has to be accelerating. But this book is just sitting on a table, like any book you might see sitting on a shelf or anywhere else. And the reason it isn't accelerating is because there's also a force pushing up on the book that is equal and opposite to gravity. And we learned earlier that we call that the normal force. So we're going to label that force, and then our abbreviation for normal force is just norm, N-O-R-M. So now there's two forces on this book. And if I did this right, which it's not perfect, but it's close, these arrows are going to be the same size because a big arrow means there's a lot of force, and a little arrow means there's not very much force. So since force normal is the equal and opposite reaction of the table pushing on the book as the gravity pulls the book into the table, they're going to be the same size, and that book is not going to accelerate. Let's try another. Here's a skydiver at a constant velocity, and it's important that we know that the skydiver is at a constant velocity. So the first thing is, if you jump out of an airplane, gravity is going to pull you down, and it's going to pull you down with the same amount of force that was pulling on that book. And again, we're going to label that F gravity. So, but that skydiver is at a constant velocity, which tells us that there's a balanced force. So even if we don't know what that force is, we're going to know that there is a vector for that force, or an arrow for that force, that is the same size as gravity, because if it's at a constant velocity, those forces have to be balanced. And from the video before, we should know that that is F air resistance. And for that, we just write F air, which is the force of air resistance on it. So when those are equal, no acceleration is happening, and he might be going 100 miles per hour, he might be going 30 miles per hour, but he's not changing velocity. He's just changing position because he's falling. Now, if that skydiver is accelerating, say he just jumped out of the plane, there's going to be a difference with these arrows. We're still going to have the force of gravity pulling down, and it's going to be the same size because that force of gravity is pretty much always the same on Earth. I'm going to label that F grav again. But this time we're going to draw an arrow for air resistance that's a little smaller because it's accelerating. It's accelerating. So that's still going to be the force of air resistance. And the reason that's smaller is because since the skydiver is accelerating, and we can assume since it's a skydiver, he's accelerating down, we know that gravity has not been balanced out. This force is big, and this force is small. So it cannot cancel out the larger force of gravity, which means there's an unbalanced force, which means it's going to accelerate downward. And we show that is unbalanced by having two different sized arrows. Now we have a football in the air after being kicked. Okay, so we're going to draw a square to represent the football. And there are two forces acting on this football. The first is gravity is acting on it, just like our skydiver and just like our book. Gravity is acting on that football. And the football is also moving through the air. Okay, so that means that it's going to have air resistance in the opposite direction of motion. Okay, and that's going to be the force of air. That's going to be the force of air. And you might say, wait, how is it moving if there's no force going in the direction that it's moving? Because the football is going this direction. But that force was applied way back here when it was first kicked. That's when it was accelerated. Now it's negatively accelerating or slowing down, so eventually it will fall to the ground and land, even if it's still moving upward. Those are the only forces acting on it. Okay, so it's slowing down. It got all that velocity from being kicked initially. A car is coasting to the right and slowing down. Now, coasting means no one's pressing the gas. If you're not a driver, that's what that means. So the car is being pulled by gravity down to the ground. We know that. And the car is not falling through the ground, so we also know that it's got normal force holding it up and keeping it on the surface of the earth. And the car is slowing down, so there has to be something accelerating it backwards. Okay, there's no force acting forwards because it's coasting, so that means no one's applying on the motor. But that's going to be the force of friction that is slowing down the car. And it's kind of complicated how that's happening. There's friction on the wheels, there's friction on the brakes, but that's the force that's slowing down the car. So it's important to note that left and right, the car is slowing down. It's accelerating backwards, so it's getting slower. But up and down, there's no change in motion. So up and down forces completely ignore left and right forces, and left and right forces completely ignore up and down forces. Forces will only add up if they're parallel. Okay, if they're parallel, those forces interact with each other, but if they're perpendicular, they don't. So now we have a book being pushed across a desk, and we're going to represent that with this. It's going to have the same forces on it from the first time we drew a book. Which are going to be the force of gravity. Do you remember what force is holding it up? That's normal force. So we're going to label that force norm. Now, you are also pushing it, so there's an applied force, because it's moving across the desk. So that's force applied. We abbreviate that APP. Now, also, there's some friction acting on it, and it doesn't tell you, so there's something you would need to know. If the book is moving at a constant velocity, you would draw an arrow that's the same size as the force applied arrow. But if it's accelerating in the direction that you're pushing it, if it's getting faster and faster, then that tells you that this force of friction is of a smaller magnitude. So if the book is going at constant speed, meaning it's not accelerating, the arrow needs to be the same size for force of friction as force applied. And if it's accelerating as you're pushing it, it's there. Now let's say that someone is pushing back on you, okay? Maybe someone is trying to push the book at you while you're trying to push it at them. Then we're going to have another arrow here, and that is an opposite force applied, okay? That's an opposite force applied. So it depends which direction the book is going, which direction friction is going to be. But what would happen is, if it is going in this direction, we would add this force applied and this friction together, and then they would be the opposite force to this force applied. So if I add those together and they're 15 newtons, and I add this together and it's 10 newtons, those are parallel and opposite, so that means that we're going to have 4 newtons of force pushing that book to the left for our net force. The force norm and gravity are equal, so our up and down forces are balanced, and there's 0 newtons causing acceleration in any direction for those. So that's how our free body diagrams connect to net force. They let us see which forces interacting. Remember, up and down forces will interact, and left and right forces will interact, but up and down and left and right will not interact with each other.